Hello, I am John McConnell, and today I will be presenting you a paper on MillWheel, which is a fault-tolerant stream processing system developed at Google and running at internet scale. So let's get into it. Okay, so what I would like to do first is go over some of the background of where we are with distributed systems and stream processing, and also, where we came from, and hopefully that will give us some insight into where things might go in the future. So I don't know if anybody here is familiar with an enterprise service bus, but JBoss, which is a native to Java, that's safe to say, service bus, right? Which is, MillWheel is a stream processing engine, and not the same thing as an internet service bus, but it's got some similarities. And this was been around for a while, and it's basically a way to get different services inside your infrastructure, a way to communicate with each other over a messaging bus. That is, there's still places that use something like this, but I would argue things are moving more towards, as we'll see in a couple of the examples, a different direction. Next, we have RabbitMQ, which is the AMPQ, which is an implementation of the AMPQ protocol, which is basically a message bus, message queuing protocol. And then now, recently you'll see a lot of people using Kafka and Spark to actually, this last one actually does stream processing. So this will, be your stream processing infrastructure. But this paper is not on those. That's just a flavor on kind of the direction we're going, as we're moving away from just establishing communication across services and moving towards stream processing. This paper's on MillWheel and Google's solution to this problem. Okay, so what was Google's motivation? So Google has a platform called Zeitgeist, which has specific business needs that they felt were not being fulfilled from the current technical solutions that existed, and therefore they decided to build their own solution, which in this case is MillWheel, which does their stream processing. So what is Zeitgeist, and what was it trying to do, and which therefore led to MillWheel's creation? It was bucketing and counting trending queries and detecting if those counts were below, the statistical norm, right? So is it an anomaly? And then also, you need to persist the bucketing and counting, because you need to be able to solve the current solution as it's running in production, but we also want to record this data, because if 1 month from now we want to try something better, we want to test out a new algorithm to check the anomaly detection, we should be able to do it. And then lastly, this data, which was doing trending for search queries, one could imagine might be important in recording the payment for Google AdWords or some other piece of infrastructure within Google, and having that would be important to get right. Okay, so on to the next slide. What are the requirements? So one is low latency. This engine should not take a large amount of time to process a single record, right? It should be able to go through the computation very quickly. It should have persistent state abstractions, to be able to transparently handle mutated state and to be able to record past transactions. It should be able to manage out-of-order messages. It should include a low watermark. I'll get into that later, but that is used to determine, the is there a part of the system that's lagging behind, or how's my latency for a given part of my graph. And then exactly once semantics, so going back to what we saw on the previous page, if this is used in any sort of payment or compensation infrastructure, you can't really mess that up. You need to get that right. And so exactly once semantics is important. And as we know, that's also difficult. Getting at least once or at most once, it's an easier problem. Getting exactly once and maintaining your performance is a much more difficult problem. Okay. So this is just a simple little slide I put together to give you a rough idea of how this thing will be interacting through this messaging and computation mode model. So what do we see here? We see some key value and timestamp. That's basically, you can think of that as a stream of inputs. So you're getting a bunch of key value and timestamps. They go to the first node. From the first node, they go to B and C. B also sends data to C. C joins A and B together, and B also sends the data to D. In this example, I made it I think that's actually a DAG, but it doesn't need to be. It can have cycles in it. And another thing that the paper stresses is that the graph can be dynamically changed at runtime. Okay. So here are some core concepts of the MillWheel framework. And here we can see a configuration of a node, right? So as we saw here, this might be node A, our configuration. And then here, instead of A, it's called spike detector. So you can see that we have two input streams and we have one output streams. And here's a way to identify the key extractor and the record format, which is basically just a way to serialize and deserialize your data. Okay. Real quickly, MillWheel has a concept of key extraction, which is basically given one input, right? I can create multiple output streams, and the way I do that is by splitting my data or partitioning my data off the key. And so I can create two streams from one, and in this example you'll see a search query for one and a cookie ID for the other. Okay. Here, in this next slide, we actually get to one of the more important concepts that MillWheel puts forth, and it'll come up later as we discuss how this compares to other things that exist. And for this, it's the low watermarks. So a low watermark is essentially a timestamp for a given node, which is basically the minimum timestamp for all future messages that it's going to see. So a very nice recursive definition of it is, for all pending work that it currently has, it's the minimum of all pending work, the timestamp of all pending work, and for all input streams to its node, the watermark for those input streams. And so we can see from the infographic below, you can see here's a node with some pending work. In the blue, you can see some completed work down below, which is black, and that line on the left, that is actually where the watermark would be. Now, if there were input streams, and the watermark for those input streams was to the left of that line, you'd have to move that line over. If it was to the right, it doesn't matter. It's the, you're taking the minimum. And then also, MillWheel has the concept of timers. This one isn't actually too crazy. This is basically if you need something to be done every 30 seconds or every 5 minutes, you can set a timer to run some user code, to get triggered during that event. And MillWheel will take care of that scheduling. Okay. So next we move on to some of the API to design a computation node, or basically to handle a record. And I think this is actually valid C++ code, which actually shouldn't be too surprising because Google kind of is known to have a fair amount of C++ code running in their infrastructure. So here we can see process record, process timestamp, right? That should be pretty intuitive. Set timer, and then produce record. So I don't feel like I should need to explain those too much. Okay, real quickly, but it doesn't seem like it's that important, although I'll make a case later on why I do think this is important. And this is the concept of interacting with, some internal system and where the boundary lies. Because when you're doing stream processing, you have a bunch of messages that are coming through on the abstraction as a stream, but you might be dealing with a legacy system, right? So we have these search queries which are coming in through this stream that are happening, quotes in real time. And then you have a relational database somewhere which has some web application attached to it and has a bunch of configuration information that you need to join with these search queries that are coming in. That's, the relational database isn't a stream. You need to come up with some way to tie those two data points together, right? And if something goes down, that this data is distributed. If something goes down, you need to replicate whatever state of that snapshot of the database was there onto another node. Or if that thing's updating the database, you need to replicate that too. And if you're running, for example, this is happening in real time, but because the data is persisted, you can replay that, right? And the data is supposed to be idempotent, right? But if you're making updates to a relational database, when you do that batch processing later on, that relational database does not have that idempotent guarantee. You need to take care of that application side. So I think this is an interesting problem to see if you can come up with a better semantics to solve this. Okay, so now more into one of the more important computation models that the MillWheel framework puts forth. When it receives a record, right, the key value timestamp that we discussed earlier, it removes duplication, right? It deduplicates it. And the way it does that is it has a Bloom filter which keeps track of messages it is currently processed. And if it sees another record come in that it's seen already, it will not process it. Okay? So for new records, it'll move on to the next step, and the next step is it will trigger the user application code, right, which contains the business logic to solve the problem. If that user application code needs to update the state, the next step will to commit those changes to persistent storage. After that, it will send an ACK to the sender of that record or message to say, hey, finish processing, and then it will forward the result of the computation, if there is any, onto the next part of the graph. Okay, so implementation. How is this solved? So coordination and orchestration is done through a replicated master across multiple modes. It takes care of load balancing, splitting up the records for a specific key and even across multiple keys. The The paper itself does not go into the exact algorithms used, but something like a replicated state machine through Paxos, and you could also include on top of this Swim to take care of membership lists would be a way to solve this type of problem. From the transparent persistent storage aspect, it does not solve this problem itself. It instead relies on infrastructure already existing in Google, such as Bigtable, and also Spanner is another. I think it's a key value store. And then lastly, this is one of the more kind of more different ones that we've seen, is a global state manager, and this one is specifically to handle the low watermark calculation and to distribute that calculation and to make it highly available for all the computation nodes. And this one is actually built as part of MillWheel, and it's to have the latency from that watermark calculation to be very low to distribute across the nodes that are currently computing the workload. Okay, so now we can see some of the results from experiments that have been run. What we see on the left is this is not a it's not a graph of frequency and latency, but it is a graph of the percentage for that latency. So here so basically the end result, or the main statistics that are gathered through the chart on the left, is that the median latency from receiving a message to sending a message is about 3.6 milliseconds, and then at the 95th percentile it goes to about 30 milliseconds. Now this is run without exactly one semantics, which when they ran the experiment with, it increased the latency by a good number. The experiment on the left shows how does latency scale as we increase the number of hosts process in the workload. So you can see the 99th, the 95th, and the 50th percentiles, and you can see that the 50th percentile remains constant, right, which is one of the requirements that was put forth for this graph processing engine, or stream processing engine. And then you can see, the 95th, there isn't any strong correlation there, but then you can see in the 99th that there is some correlation, right? Which is kind of expected, because the more dependencies, the bigger that you have with your computation, the more likelihood that one of those dependencies will fail and will spike, right, your latency, which is, important to kind of realize too, that, you see this constant median latency, but what is unknown is, how this might be affected by the depth of the graph to do this computation, right? Because if you have, even though you have 99, you might have a 99% success rate, the overall success rate of your system is 1 minus, 99 to the nth, right? Where nth is the number of independent trials that you have. So this 99th percentile spike might actually be important for more, I guess we'd call them for deeper computations. Okay, so in this next experiment, you see the amount of lag it takes to propagate the watermark across the nodes. So in stage 1, that you can see that the latency is about 1.8 seconds, and it grows by about 200 milliseconds for stage 2 and stage 3. which the authors have concluded, which was fast enough to meet the requirements. And we'll actually see later some argument why this was important compared to a heart beating mechanism. So next on to caching. So when we look at how MillWheel is doing its computation, when it updates its mutable state, you have these records come in, they do a little transform, and maybe they do a little change of state, right? And so you have all these writes coming in. And then after a certain amount of time, MillWheel will try to aggregate the end result. And so, if you think about it from a caching perspective, you got all these hot writes coming in, which are basically updating your cache, right? Because they're very recent. And then you have this cold aggregation. So, a lot of a very popular algorithm for caching is LRU, which is least recently used. So that kind of hot write, after a while, very cold read does very poorly. So the MillWheel authors decided to implement their own cache as part of the MillWheel architecture, and recorded the amount of CPU usage as they increased the cache size. So basically here there is no cache, and the unit is 1. There is no unit, right? Just the amount. And then as it increases, as the cache increases, you see that you can get down to about half the CPU utilization. Okay. So related work. MapReduce is one of those frameworks that has been around for a while, right? And it's been used to kind of, historically it kind of jump-started the way to scale out your computation model, right? To get it onto many different nodes. But it has a very, rigid semantics behind it, right? So if you're using it for something like word count, it's great. If you're doing something more complicated, you kind of need to chain a bunch of MapReduce jobs together. And so people have been trying to migrate off it and move to something like Giraffe or GraphX or Storm. And now recently we've moved to Spark streaming. And one thing to also keep in mind about the previous MapReduce and Storm is that they do not provide that exactly once semantics. With Spark streaming, they do provide the exactly once semantics. But as the MillWheel authors argue, is that even though it provides the exactly once semantics, it does not provide the latency and performance that they're looking for. And if you're looking into the reasoning behind that, is that the MillWheel authors talk about that low water point global state manager. And so, the other solutions that have been proposed to do that same computation, that low watermark calculation, they attach some metadata to their message, and then the hosts, the nodes on the network try to, recombine that metadata to come up with a consistent watermark. This does not do it, right? This has that global state manager, and they argue that's a more that decreases the overhead and makes the computation faster. So it'd be interesting, as far as future work, to kind of test that out by perhaps patching, Spark or putting it on a different stream processing engine, right? And see if you can get comparable results, which is the argument the MillWheel people are putting forth. And one more thing too is that the main algorithm behind doing the stream processing, which is this sort of mini batches of messages and checkpointing, originated, or at least the authors of these papers point to that it originated in a paper by actual Michael Stonebreaker which you can look up to if you're interested. Okay, so looking towards future work and other things that might be worth exploring. There's always different semantics you can try to come up with on how the actual software engineer who's solving the application problems is going to work with your system, which provides the exactly once guarantees and the latency guarantees. You can always come up with a different type of way you interface with that code. Again, also, trade-offs of performance, you can look into something like that. One thing that, I find kind of interesting, and I kind of talked about it for a while, was the handling of external systems. Very rarely, I would argue, do you build something in isolation. Usually you build some stuff to solve some needs, and then you glue it together with other things which are currently existing. So gluing together a stream processing engine with existing applications, at least in my experience, has been an area that's been more bug prone than other areas. And thinking about it a little bit more broadly about and especially in terms of the perspective of an operating system or operating systems, you look at something like MillWheel, and it's a way to orchestrate and to scale out pieces of computation, right? And when you look at an operating system, that is a way to orchestrate and to manage your processing. So if you can find a way to tie together the idea of a process and inter-process communication and isolation and all those very difficult things, it would be a very tough challenge. But if you can get a way to interact with a big cloud of servers and to abstract it and to make it transparent as like this is just your workspace, that could be pretty powerful. Although that would be powerful. It just I don't it might it's probably pretty difficult. So with that, I'll end my talk and have a good day. Thanks.